Well, hello everyone. Welcome to Zen and the Art of SOLIDWORKS Surfacing. My name is Andrew Lowe. I'm a senior industrial designer with the Damani Group. The Damani Group is a full-service industrial design engineering, electrical engineering, and software development consultancy. We're located just outside of Chicago, Illinois. We have lots of experience across a bunch of industries, most notably commercial industries, gaming, life fitness, and the commercial industry, both software and hardware development, tools, hand tools. We offer 3D laser scanning. We're active in the railway industry. As well, we have our own prototype labbing, so that way when we make mistakes, we get a rework. Who am I? I'm a senior industrial designer with the Damani Group. I collect mid-century design. I build custom coffee tables. This is my 7th time presenting at SOLIDWORKS World. Also, plug. These are the coffee tables I make. Lowe Design Company. We turn wood and metal into functional art. LoweDesignCo.com. Check it out if you feel so inclined. That's with the end of the plug. Let's get started. So I want to start out with a question to all of you. If you were a limo driver, what would make a smoother ride for your passengers when you're making a left-hand turn? Sharply turning the wheel, holding it to the exact radius of the corner you needed to go around, and then quickly yanking it back as soon as the turn's done? Or if we gradually turn the steering wheel to the desired position to negotiate the turn, and then we gradually unwound the steering wheel back to straight. Well, we know that this is going to make a smoother ride for our passengers. So how does that relate to SOLIDWORKS? Well, it relates to all kinds of surface and solid modeling in continuity. And continuity describes how surfaces are connected to each other. We have 4 kind of fundamental types of continuity. You can go up higher, but ultimately, when you get that high, it doesn't really matter. So we have G0, which is we have 2 surfaces coming to a connection, but there is no smoothness between them. There is a sharp edge. We have the G1, or tangent condition. If you ever put a standard fillet on a model, you get this kind of connection. There is the next level of connection, curvature, or G2. If you've applied a curvature continuous face fillet, or in 16, I think they added the ability to make standard edge fillets curvature continuous, you've got this kind of connection. And if you manually sketch something with a spline, you might get a perfect G3 connection. And what does this actually mean in the real world? So we'll jump into SOLIDWORKS, where I have these 3 kind of connections modeled. So here we can clearly see the sharp edge of the G0. And with the G1, the tangent connection, we can actually physically see where the fillet or the transition starts and stops. So if I run my mouse over, we can kind of see the edge here, and we can see the end of the fillet here. And they line up perfectly with the edges of the fillet. So we can see a hard break in the light transferring over the surface. If we look at the G2 connection, it's a little bit smoother. We don't really see the hard start and stop of the fillet. And then finally, the G3 kind of looks the same, but if we start rotating the view, you can kind of pick up the difference between them. Now, functionally, these surfaces are almost identical. If I turn back on our edges here, we can see that there is very, very little deviation between the 3, short of the G0 connection where we have that hard edge. But if we rotate the view back, one thing to note that as our transition improves in quality, it needs to become larger to visually look the same size. So visually, these transitions look the same size, but we can see that the actual size of the transition, the distance between the edges, increases. And I found that factor is about 1.4 times for each level you go up. So if this was a 1-inch fillet, you'd want to go to a 1.4-inch curvature continuous fillet, and if you were creating it yourself with a spline tool, you'd probably want to go up to about a 1/8-inch radius and then build the spline-based transition between them. So another way we can look and evaluate the surfaces is with the continuity tool. When this is the curvature, here we just see the standard surfaces. So this is just showing the rate of change. We can also use the zebra stripes tool, which we'll take a look at a little later in the presentation. So where am I going with all this? Why does continuity matter in our surface models? Well, it matters is because high-quality surface models are never made from a single surface working overtime. Instead, they are carefully crafted from a network of surfaces where each surface is doing the least amount of work possible. We want our surfaces to be entirely relaxed. We don't want them to bend too much. We don't want them to undulate and form if required. We want to build lots of really gentle, relaxed surfaces, but we need to connect all those surfaces together. And the way we do that is by ensuring that we have the right level of continuity between the different surfaces such that we can't see the transition between them. The network of surfaces is imperceptible if we were to take the model edges off in SOLIDWORKS. We wouldn't be able to tell one surface started and the next stopped. So in order to build these high-quality surface models, we need to understand the network that connects them. This network is often referred to as the patch layout. Some other people might have some other terms, but that's what I refer to it as. We'll delve deeper into this later in the presentation, but to give you a quick idea, primary surfaces are large and flat, and they're going to be the first surfaces we construct. These are the blue surfaces on this Eames shell chair model. Blend surfaces connect primary surfaces together. So these are kind of, you can think of them as fillets, but not really fillets. And then transition surfaces are kind of the hardest, most complicated surfaces to make, so we'll save them for last, and they complete various regions of the chair. So in order to have great surfaces, we have to start with great curves. We need those great curves and underlying geometry to get really good surface geometry when we jump into surface modeling once we've created our sketches and our curves to build our surfaces with. So what does this level of connection actually look like when we're starting to sketch splines? So tangency, we have the G1 connection we talked about before. And when we're evaluating with the curvature comb tool, which is showing the rate of change of or curvature of the surface, so the radius is actually changing along here. If we were to look at the G1 connection, the curvature combs are all the same height because arc has a constant radius. That's why it's an arc and a radius. So the angle of the curvature combs are equal in the G1 connection, but the length of the curves is not. And this is going to give us that hard edge, just like the fillet showed. We're going to see a break in the light lines, or the quality of the reflection of the surface. If we go up to the next level of connection, the angle and the length of the curvature combs at the junction is equal. So that's going to give us that smoother transition. And if we want to take it one step further to that G3 continuous connections, both the angle, the radius, and the change of the radius are equal. So we see that really smooth ramp in compared to the G2, where we get that really sharp acceleration. Here we're getting that really nice, smooth, gradual acceleration as the radius of the spline here increases and then decreases back to 0, such that it can become equal curvature, or G3 continuous with a straight line, because a straight line obviously has no curvature. So how do we go about creating these really nice curves and surfaces in SOLIDWORKS? So I'm now using the Style Spline tool. When it came out in 2014, I thought it was a game changer in surface modeling. The math it uses in the background is a little bit different than the classic spline tool. This means that it's far less likely to get these kind of spikes. You get a very smooth transition in your curvature. Whereas with the classic spline tool, if you keep it to 2 points and just manipulate it with the handles, you're good to go. It's going to be good. If you add a third point, don't mess with the little middle button. Don't do this, because you get these weird kind of humps and spikes in your curvature. If you do need to have a third point to better control the shape using the classic spline tool, just add that third point, but never play around with the little handles here. So going into SOLIDWORKS, what does this actually look like when we're sketching? So here we can see the classic 2-point spline. The curvature is going to stay nice as long as we just move the handles. So we're familiar with the spline tool, not going to spend too much time on that. But the multiple point spline, so here I sketched a spline through a bunch of points instead of manipulating the handles, and you see it's got a kind of a flat spot in the curvature. So if you are sketching with the classic spline tool, just try and use the handles. Here is multiple handles, and as soon as I started manipulating, I've got a really sharp crease in my curvature here. And if I was to extrude the surface, and let's just take a look what that actually looks like. If we move the view, we can see that line reflected in the reflection. I don't know if it's entirely clear on the projectors, but trust me, it's there because the curvature combs don't lie. Another way we can expect this is by right-clicking and surface curvature combs. This was a new feature they added somewhat recently. If we go dynamic, we can click, and the graphics window is not showing it for whatever reason, because SOLIDWORKS, and sometimes it doesn't work. But trust me when I say that, in that you should be able to right-click and surface curvature combs. Let's go persistent and pick the face, but it should show them to you. I don't know why it's doing it. But here, we see the mouse over, that spike in the curvature is there. So this is why I'm a fan of the Style Spline tool. No matter how much I move these points around, I'm never going to get a spike or a divot in the curvature like we saw with the classic spline tool. So I'm using the spline, or the new Style Spline, as much as I can when creating outlines for my surface models. I just find it just easier and nicer to work with. There's a lot of content on the internet and some of my previous presentations about working with splines, so I'm not going to spend too much time on it today. What I do want to mention is, we saw this, don't do this either, sketch with a bunch of points, manipulate the handles. Do want to mention a couple things that I change out of the defaults to make it a little bit easier. I changed the temporary graphics shaded. This is normally yellow, and I find it's kind of hard to see on a white background, so I change it to this nice purpley kind of color. And the other thing I do is under Sketch. This is actually something I learned at SOLIDWORKS World. I didn't know this feature existed, so that year was worth its money. Show curvature comb bounding curve. So what this does is it puts this nice little smooth line on the outline of your curvature comb. Previously, I just cranked up the density of all these different lines, so I kind of had something that showed this, but I find this is just a way nicer way to do it. We don't have to have as many porcupine spikes in the curvature comb. We can just have this nice smooth bounding box around it. So that's under Sketch, Show Curvature Comb Bounding Curve. So this is kind of a holy grail that I've heard a lot of people talk about, parametric G3 connections. We saw that the G3 is the smoothest way to connect geometry together, but SOLIDWORKS doesn't support it. It's got tangency, it's got equal curvature, it's got curvature continuous. It doesn't have this G3. However, I noticed something when I was sketching with the spline tool. I was able to create a nice G3 connection manually by adjusting the points. But you can see in this image, the points are blue. They're underdefined. So when I make a dimension change, and this is just the way the SOLIDWORKS sketcher happens, I wanted to change this sketch from 3 inches to 4 inches. Well, the points in the style spline that defines its shape stayed in the same position. So now the points that define the spline are over here when they should have moved proportionally with that. So it's just a flaw in SOLIDWORKS. It's just the way it works. So we need to get a way to have these points move in relation to the spline itself when we make parametric design changes. So how do we potentially go about doing that? Well, we need to control the degrees of freedom of the style spline. So going to SOLIDWORKS, we can demonstrate this. So one thing I noticed when I was creating some style splines, so I'm going to create the style spline, and the style spline needs at least 2 points, although it doesn't work ever between 2 points, so I just kind of roughly, we created a classic spline. We don't want that. We want the style spline. So it needs at least 2 points to work. You can't create it between just 2 points. So there's the first point, the third or second point, and the third point. Now it works. So I'm going to make it tangent to this sketch line here. Perfect. And it also added, and when I add the tangency to this sketch line, it's also going to add a second point. The tangent needs at least kind of 2 points or 3 control line segments. But notice one thing it did. It might be hard to see, but this line is fully defined. I can't change its angle. I can change its length, but I can't change its angle. Interesting. Likewise, on this side, I can't change its angle. Its angle is defined when I added the tangency relation. So let's go take that a step further, and I've got a style spline here, but we're going to redraw this one. And I'm going to make sure that I have at least 4 control line segments, so I can change that by changing the curve degree, or you can right-click and insert control vertex and just pick anywhere, and now you've got another. I don't know what these are technically called. I just call them control segments. The actual points are referred to as spline control vertex. So let's go ahead and add the tangency relation here between the spline and the line. Perfect. And now let's take it a step further and add equal curvature. Now, what happened there? Something jumped. If we just zoom in, we took up another degree of freedom. So the curvature continuous relation needs at least 2 degrees of freedom. If I do that over here and go equal curvature, likewise, these 2 line segments are fully defined. Tangency, we had 1 line segment that was fully defined. Curvature, we had 2 line segments that was fully defined. What if we go 1 step further? Take up. So we're going to go perfect G3. Let's take a look at this sketch. So here I was able to create a perfect G3 connection. And the way I did this was creating 3 line segments in each portion of the curve. So I've got 3. And notice that the angle of them in the previous examples was always equal to this line segment here. So what I did was, instead of adding the tangency or the equal curvature relation, I selected all three of these line segments, and sometimes you really got to zoom in, and I made them collinear to this line segment. And now, with the three line segments all collinear here, I've got that really smooth acceleration of a G3 connection. But the points are still not defined. Remember, see, if I was to change this to 4, we're going to see the same situation as the screenshot. The points don't actually move along the curve proportionally. Because they're underdefined, they stay exactly where they were in space. So how can we potentially make the lines move in conjunction with the spline? Well, one way I came up with was I took all the line segments after I'd made them collinear, and I made them equal to each other. So now they're proportional. So now when I make model edits, these all have to stay the same, such that the control vertex points have to move in relation to model edits. So if I were to go, say, 3 1/4 here, the spline moves along, and I still maintain that perfect connection. 3 1/2. One thing to note, and this is just a weird bug I found, is if you need to make edits, you kind of got to inch it along a little bit, or 1/4 inch it, or 1/2 inch it. Say if I was to go to 5 inches here, it worked this time. Sometimes it doesn't, and the spline just blows up. The points don't move in space, but if that happens, let's try and get it to break. Let's really move this. Oh, so now it's behaving. When I was practicing earlier, it didn't behave, but that's just SOLIDWORKS for you. But sometimes the points don't move, but there's a fix. If they don't move, all you've got to do is just exit the sketch. This will all be red and yellow, look like ketchup and mustard, but just exit the sketch and do a Control Q rebuild, and that should wake it up, and the point should move. One way I found was that, so I guess in the sketch it was working, but if, let's say, I double click and I'm not actually in the sketch here, and let's go 7. Let's see if I can do a little rebuild. Yep, perfect. So this example is working. This is great. It wasn't working earlier. So all I want to say is this is a perfect way of doing these nice parametric, really smooth transitions, but you have to treat them cautiously just because sometimes the control vertex points wants to stay locked in space. So let's take this a step further. We figured out a way of making parametric connections to straight line segments. It's pretty simple. All we do, and well, actually, why don't we just demo that so I can show you how simple it really is. So we'll start a new style spline. I just kind of like sketching a couple points. Then I'll grab the spline and I'll change the curve degree. We want to go up to 6. That gives me roughly, or that gives me the number of control segments I need. I'll select them all. We'll go collinear. We'll unselect that and we'll go equal. Perfect. Now I'll drag these over. And here I got to really zoom in to find that line. Grab the line segment and let's go collinear. And then unselect the line segment and go equal. For whatever reason, it didn't fully define itself, but see, I can't do it. So it is fully defined, but for whatever reason, I've sometimes run into this. It doesn't actually define itself, even though I can't move you in space. But super simple, make the control segments collinear to straight line segments, you can get G3 connections. It's a little bit harder when we use an arc. So here I have 2 arced line segments. I've defined the size of the radius I want to have with just the standard fillet tool. I find this is a great way of easily dimensioning the size of spline-based blends. Just define the size with the standard fillet tool. And then I just have a habit of converting into the next sketch. So what I had to do here, this was a little bit harder to set up, and I'm going to redraw it for you. But essentially what I did was I added the equal curvature relation. I can't use the collinear because we can see that these line segments are not actually collinear because it's an arc. We can't just make it collinear. So what I did was add the equal curvature relation to each end, and then I massaged the spline to where I needed it to be. So we'll just draw that spline again. And we're going to go 6 degrees, perfect. Now we're going to select the spline, not the line segment, and we'll go equal curvature. We'll go equal curvature. We'll turn on our curvature combs. So now I'm going to move the points manually. Like I've got something looking pretty good over here. This side needs a little work. So I probably want to move this first guy up. So that way it's got a little bit more room to accelerate. Maybe keep. So this is a little trickier. We got to massage it just to get it right. but now I'm pretty close. Let's just call it a day there. And now the way I'll fully define this, these line segments already look pretty similar, so let's just make them equal. These two also kind of look like they're about the same distance, so we'll make them equal. And then we'll finally define this with some angle dimensions. No actual number dimensions. We can use angles, but if we start using dimension numbers, we're not going to be nearly as parametric. We've got 10 there, and these are actually pretty close. What happens if I make a collinear? That moved, and finally, we might want an angle dimension here, 40 degrees. Now we've got a black parametric G3 spline, so we'll exit out of this. I found that these arc-based splines are a little bit more prone to blowing up when we make changes, so we just move that to 3.5. Look at our sketch, perfect, it moved. Let's go 5 here. I'm hoping I blow it up. So we'll do a rebuild. Yeah, we got that question mark. So what happened here was the points didn't move in space. The points are exactly where they were. There's no reason why they should be there, but the solver just says, it gives up a little. So let's try that Control Q rebuild, try and wake it up. Nope. Control Q, nope. So the only way to solve this is to undo. And it's still blown up. Actually, no, it's in the wrong spot. It needs a Control Q. And now we're back and not overdefined. So if you do create these parametric arc-based transitions, what we want to do is a little bit at a time. Cool, it moved. So we got to 3.5. Let's try 4. No, blew it up. So you got to be really careful with this. You got to move it a little bit at a time. It just goes to show you that if you want these really, really perfect G3 connections, sure you can do it parametrically, but yes, it's a lot of work, and you got to really be careful with them because they have a tendency to blow up. So if there's any developers in the room here and you're listening, all you guys submit enhancement requests. We want that G3 functionality. So just to recap, the number of degrees of freedom is kind of defined based on number or the level of the connection. So that tangent, we take up 1 degree of freedom. The G2, we take up 2 degrees. The G3, we take up all of the 3 degrees. So if we're just making straight lines, it's really simple. Just make collinear. We can add the equals relationship. If we're making it to arcs, we got to do a whole bunch more setup work, which is sketch the spline, drag the points, make it look nice, add some angle relations and some equal or collinear relations, and we're in business. We now have a G3 connection between arcs. So what that kind of means in the real world is it's really easy to create these really nice kind of iMac, Apple-ish looking forms that are parametric. And because I'm lazy, I'm only doing 1/4 at a time. But I now have this nice parametric model driven here, and this is where it's going to blow up. So if I want to make this a little bigger, I just got to scooch it up. Got it. But if I were to really move it at the same time, I'm not going to show you how I model this little recess. And I've also got another example, but these files will be available. Run through the feature tree. Take a look. I just really wanted to make you aware of how difficult this is and how prone it is to blowing up. But if we were to turn off the lines, we have this really nice kind of seamless transition on the corner of this. Got a really nice soft kind of pillowy shape that's all the rage in consumer products today. But to show you that it blows up, oh, that's not the sketch I wanted. We want this one. Let's go 7 inches. Oh, it works. Didn't work before. One last thing I do want to make you aware of when working with splines is it takes a little bit more work, but you get way better outcome, is that when we're offsetting splines, it never works well. Whatever math the offset uses, it's not good. So here I created a cut and I used a sketch, or I didn't use an offset, I sketched it. But what really will show this is I'm defining this transition with a fillet here, and see how pinched this gets? The bigger I make this fillet, the more pinched this is going to get. So one thing I do is I come in, I delete the face, I add a split line with just a manually sketched style spline. And to make this parametric, I just make all of these control segments parallel to the kind of the master curve that defines the outside here, and you'll get a nice parametric spline, and it kind of rounds off that sharp corner, and you get a much better transition. So actually, real quick, we're ahead of schedule, so why don't we actually take a look how we made this. So here I used the fillet tool to just define a set of edges. This was just a quick way of me getting this edge. I want to make this kind of scalloped shape on the top of this whatever Wi-Fi router, IoT home device. So I'm using delete face tool to delete those faces I didn't want in the model. For those of you who are a little new to surface modeling and you're afraid of it, just start with solids. Solids are great. They're our friends. They work really, really well. And then we can clean out the bad faces we don't like, and then we'll create surfaces in between. So now you can see I've kind of got an area that I can build some new surfaces in. I clean up that bad corner, the kind of pinched corner from the offset. Delete face instead of a trim, just one way of doing it. And finally, we'll use the workhorse of surface modeling, the boundary surface. It's great. It's perfect for building four-sided style surfaces. And a lot of the surfaces we want to build are inherently four-sided. And instead of building one big surface that has to do too much, I'm going to build three smaller individual surfaces because I want them to be as relaxed as possible. So this was just a matter of picking this edge and picking this edge. One thing to note is that, remember when I said that the curvature continuous connections need to look a little bigger, that 40% kind of factor? Out of the box, if we turn on the curvature combs to show us what that default 1 value, tangent direction is what SOLIDWORKS calls it. I just kind of call it the inflate button because here we can see a big spike in the curvature. We want that to gradually accelerate, and I found that 1.4 is kind of the sweet spot. We still have a little bit of the dip in the curvature. If I wanted this to be absolutely perfect, I could have created a sketch and done that G3 style connection, but for the sake of this example, this was good enough for me. So I created my first boundary surface, I created my second boundary surface here, and now it was just a matter of creating the third one to finish that corner. One thing to note is, yes, I picked curvature to face here, but I did not pick curvature to face in either of these directions because these curves here and here are already curvature continuous. I don't need to give SOLIDWORKS that little bit of extra information. It's already inherently going to be curvature continuous. One thing I did have to do is I didn't have that little tangent direction value, changing it from 1 to 1.4. So what I had to do was increase the tangent influence. So if I have profiles in both direction 1 and direction 2 of the boundary surface, it changes that to tangent influence. And this is just kind of how much do I want the shape of this surface to influence this surface. And a lot of the time you want it to be 100%. I find it kind of just pumps up the surface. It makes it look a little bigger. It's got a much more gradual transition from this surface. And that's what we're going for, that nice smooth kind of connection. So now I've got my surface model. One thing to note that the defaults are red on surface edges. I happen to change them to red just because that's kind of the way I've always worked, and the red just looks a little nicer, I find, on the screen than the blue. Your personal opinion. Make them green, make them orange. It's your choice. So now to get this back to a solid, let's use the surface knit tool. This just kind of joins everything together. We go from those red open surface edges to the dotted solid edges, and now this was a great new feature they added. I don't know, it's like 14 or 13. It was the intersect tool. So what I do is I pick the mirror faces because ultimately I'm going to mirror this because I'm only doing 1/4 of the work because I'm lazy. And so I pick the front and the right planes, and then I pick my surface body, and I hit this little button, cap planar opening on surfaces, and I get a solid out of it. Yay! So I didn't have to use a planar surface, pick all those edges. I didn't have to use a surface fill. I can just use the default planes, the intersect tool, and then a couple mirrors, and now my nice little smooth pillowed shape with a scallop top is done. So what if I wanted this to look more like an apple thing? We got that very smooth kind of sculpted top. It doesn't come to a filleted edge. We have that sharp corner. We've got that nice kind of shape. I don't really know how you call it, but everyone's seen this before. So let's turn this back a little bit. So instead of building a scallop, I'm going to build a pillow shape. So the way I'm going to do that is I'm starting with a cut. Before I start surface modeling, I'm just cutting material away. So I'm creating a cut, and this generates two new sets of edges. I didn't have this edge before. I didn't have this edge before, but now with the cut, I do. delete face to delete the extra faces in the model. Finally, boundary surface. So this is just the reverse of what we did before. Instead of making it it's scalloped and indented, we're just kind of making it the reverse direction. So here I'm going edge curvature. Once again, we're picking that 1.4. It's not absolutely seamless. There is a bit of spike in the curvature. Once again, if I wanted it absolutely perfect, I could manually create a spline here and here. It's good enough for what we're doing. Likewise, I'm going to do the opposite corner. And then finally, so here we just kind of built the reverse of what we built before. We just kind of flipped it over, but it was built in the exact same way. But I was able to start with a cut here to define the extra edges. Once again, we'll knit into the model. Let's mirror, turn off the edges, take a look at that really easy to create, nicely pillowed model. We can use the curvature tool. We have a nice, really clean transition. We don't see a hard break in the curvature, means that the curvature of the surface is gradually accelerating. And you can also use the zebra stripes tool to evaluate. The zebra stripes, imagine if we took this object, it was perfectly mirror reflective. We put it in a room like this, but instead of these rows of lights, we just had bands of big fluorescent tubes. We would get this kind of nice stripe lighting, and we don't want to see any kind of hard break. We don't want to see a hard line. We want to see a nice smooth transition. So if we don't see a break here, we know we've got our tangent or our curvature continuous connection. And we built our nice little pillow shape. So this is a quick run through of some of the surface features and how and when I use them. Surface extrude. This is one of the first surfaces I'm going to build in a surface model, and it's got a purpose as a reference surface. So if I'm designing a part that's going to be injection molded, this is definitely the first thing I'm doing, is because I want to make sure that I have the right draft built into my surface. I can't necessarily use the draft tool on surface features, so what I do is I build this reference surface, make any surface that comes to the parting line tangent to the reference surface, and bam, I have whatever degree of draft is specified in this feature. And if I need to change the draft angle, maybe we wanted a deeper texture, it's just a matter of going in and changing that draft value. Likewise, if I'm creating something that I know is going to be symmetric, and I'm only creating half of it because I'm lazy, then I'm going to build a reference surface, but I'm not going to have any draft. Anything that it needs to be tangent, or it's going to get mirrored, will become tangent with that reference surface, such that when I mirror it, I don't have a little a hat, or I don't have a divot. I'm going to have a nice, smooth, flat connection at the mirror plane, and we won't be able to see any issues with our surface. Touched on it before, but the boundary surface is going to be the workhorse of surface modeling in SOLIDWORKS. I find used to be that older people who have been using SOLIDWORKS longer than me, which is what, 12, 13 years. Loft was their go-to just because it's been around. I just prefer boundary surface. It does have one benefit over Loft in that it supports curvature, continuity, and direction too. So the best practice, we always want to create boundary surfaces that have 4 sides. 3-sided and 2-sided boundary surfaces, they're not good. They create this thing called a degenerate point, which can really cause issue with shells, fillets, offsets. Another way we can build the boundary surface instead of using a network of curves is it works just like a sweep. So I have a direction I want to sweep something along, and I have a profile I want to sweep it along. Something to know. It works great for building transitions in between surfaces. It also works if you only have 2 profiles. I didn't really know what this bottom edge of the surface wanted to be, but I can go from this profile to this profile and tell it needs to follow this too. And it also can create surfaces from a number of profiles. If you use this little button, Trim by Direction 1, what it's going to do is actually not use any of this information over here. So even though this profile is all this long and this profile is this long, it's only going to add surface material between this profile and a profile I have over here. It supports continuity in both directions, so I add curvature to face. We can use the curvature combs to see we get that really nice, smooth, gradual transition. That tangent influence slider I mentioned, we want to increase it to 100%. A lot of the time, it kind of pumps up the surface. We don't run into this little flat spot here, so 100%. Finally, the surface fill. The surface fill is probably the most powerful feature in SOLIDWORKS, in my opinion, because it gets you out of trouble and little modeling situations that when you're painting yourself into a corner, surface fill is going to get you out of it. So what surface fill is great at is generating surfaces between n number of surface edges. So here I had this situation where I had 5 different edges I need to bridge. And we know that 5 edges, well, we can't really do that with the boundary surface or the loft. But what the surface fill does is I pick the edges I want, and it builds a big 4-sided patch. And this yellow grid preview, this is an old screenshot. This is from 2014. In 2015, they got rid of this yellow grid preview. So I don't know why they did it. If a developer's in the room, we want it back. At least I want it back. But it shows you what that 4-sided surface is going to look like. And then we can see that it gets trimmed back to fit in this region. So it's a great way of 3, 5, 6, 7, 8-sided patches you need to get yourself out of. Use the surface fill. It supports both tangents or contact, which is the G0, tangent, G1, and curvature in all directions. And we'll take a look at using that a little bit later. One thing to be cautious of is we talk about curvature. We want to have that nice G2 connection. But if we add too much G2, too much curvature to the surface fill, you can get little pockets and divots, not so nice. So start tangency on all edges, then use your zebra stripes, use your eye to see if there's a break in the light line, and add curvature only as required. We'll look at that a little bit later too. So here's the analogy of imagining what's the difference between boundary surface and surface fill. Imagine the outline of the patch as a frame with a rectangular tarp stretched over it. The tarp can be any shape and size, but it always has to have 4 sides. So trying to fit the tarp into this shape causes it to bunch up. That's that degenerate point that I referred to and what we want to avoid. So draping the tarp over the frame and then kind of tucking it under the edges, that's more what the surface fill is going to do. So when do we want to use the boundary surface? We want to use the boundary surface when we have a nice 4-sided or 2-sided. Really, we want to generate 4-sided geometry ultimately with the boundary surface. Surface fill, we want to use it to get ourselves out of tricky situations when we have 2, 3, 5-sided surfaces. So here we can use the curvature or the zebra stripes, not the curvature stripes, the zebra stripes to evaluate connections. Here I have a really nice G2 connection here. But if actually we see over here, this technically maybe isn't G2 because we see a little bit of a more hard line. The stripes connect, meaning they're at least tangent. If they weren't touching, that would indicate G0. So we can build the surface fill and then evaluate with the zebra stripes. We can also evaluate with the curvature display, but I prefer to use the zebra stripes to evaluate. So I want to jump into 3 different case studies with the roughly hour or 50-ish minutes we have left. So solid sculpting. I find this is kind of the easiest way to start with something when you don't exactly know where you want to go. So I call this subtractive surfacing. I'm going to use as many solid features as possible and only use the surfaces where required, which ultimately was pretty much every single face you see on this model, but it still started with a big solid feature. And then I sculpted this shape with the surfaces. So let's take a look at how I went about doing that. So I had a sketch that I'd started with that I wanted to kind of meet, nice hand sketch. And I knew that there were some significant character lines on this electronics enclosure. So we have this outer perimeter that I want to emphasize. I have this kind of flat surface on the top. There was some electronics in here that needed to have it this size. So I emphasized this kind of pink character line. Then we had an angled face, an LCD, ultimately goes over here. So I had this other character line, kind of hard edges on the model, and then finally this 4th character line at the back. And those were kind of the hard edges on the model. Everything else was smooth surface features that we wanted to connect seamlessly. So the first thing we're doing to do is start kind of creating sketches for our character lines. And what that is going to allow us to do is here we can see the completed model, nice shape. Can't really tell you what it does, but I can show it to you. So here we have sketches that I've started on the top face of this model. One reason I love working with solid features is I get a whole bunch of faces that I can build sketches on. If I didn't start with the solid, I'd have to create planes, I'd have to create a bunch of curves and sketches, but solid features give me edges, they give me things I can reference. So I created this sketch, and then what I did was created a sketch that's really going to emphasize this front surface. So if we were to go normal and take a look at this guy, instead of just drawing a straight line between this point and this point, what I did was I created a little bit of a straight, and then I created a style spline, made it curvature continuous here, and I just kind of kick it up a little bit. And what this is going to do is really emphasize his character line. If you study a lot of the lines on cards, you'll see that they do this to really emphasize the hard character lines that are stamped into the sheet metal of modern car design. So creating this surface was actually really easy. if we turn off our curvature combs, we'll see. So I have a sketch here, and it's just a straight line. I'm not actually going to build the fillet in at this point. We're going to do that second. So I have this sketch here that I'm using as a profile, and this sketch here that I'm using as a profile. Created a plane here and just used an intersection curve to get these sketch lines. So this was really simple. It was 2 sketches with my third profile, and this kind of act like a sweep. And unlike, well, I guess the sweep feature works in both directions now, but technically these lines are not parallel. They're at a bit of an angle to each other. So the boundary surface, great way about going about creating this surface. So now we need to actually get that into the model. One thing I found when I tried to do a surface cut was that the edges weren't quite long enough. So I added a surface extend, make that a little bit longer, and then I come in with my cut and I remove the material. So now we've sculpted the front face of the model. And I like to refer or think of SOLIDWORKS models as campsites, leave them clean. So one way of doing that is using the body keep or delete feature, and we want to delete the surface bodies when we're done. No use for this anymore. We cut with it. So that way at the end of my tree, I don't have a surface bodies folder with 42 surfaces in it. I'm also a big proponent of naming features such that the next guy who's going to work on this at least has a little idea of what each feature does. So I want to round up the corner. I'm just using the standard fillet tool here with the curvature continuous option. Nice smooth transition. But if we were to look at the front of this model, it's kind of hard to see, is that the fillet tool actually kind of caused this edge to kick up. So we've got to go in and fix that. So some of you might say, oh, I know how to do that. We're just going to add a split line here. We'll add a split line here. And that'll give us a new kind of profile that we can create a new boundary surface between straightening out that edge after we trim it back. I'm going to say, I used to do that. That would have been what I would have done 2-3 years ago. But I think there's a better way, and that is the split tool. So instead of using split line, which splits faces, split tool splits solid bodies. So I now have 2 separate bodies. I colored them green for the new body. And what I find is that if I need to change the design intent at some point for whatever reason, instead of having to try and delete the split line, which is terrible for parent-child, all kinds of things can get attached to a split line for whatever reason. If I need to get rid of this, all I do is combine it back together, and all those lines are gone. So a really easy way. So you still have the split in the model, but the rebuild on the split's next to nothing. But now that it's split out, I will use the delete face. And I am using a split line here simply because I can't trim this edge with the surface trim because it would also trim this edge back here. So I split line it, I use delete face, and now I've got a really nice straight edge here. I've got my edge here. It's just a matter of dropping the boundary surface in between. So we're adding the boundary surface. Remember, I don't actually need to use the curvature option here because this edge is inherently curvature continuous. Because this edge is inherently curvature continuous, I'm good to go. No end conditions here. Now it's a matter of knit into the model, and we combine, and those edges also disappear with the combine. And now, when I hide these sketches, because I have no use for them anymore, I've completed that sculpted front edge. And you can see that little white highlight here. If we just had a flat face, we wouldn't get that little highlight there. So if we want to really emphasize character lines on the models, try to think of including a little bit of a kick up, a little bit of a ramp to have the light reflect off that. So to recap, we identified the character lines. We sketched the surface profiles. I'm using that fillet trick to define the size of my transition. I'll come back in with the style spline so I have a G3 connection. Remember that the smoother the connection, the smaller it's going to look. Here is the tangent arc, and here is the G3 connection with the trick we talked about. All 3 line segments made equal and made collinear to this line here. Likewise on the other side. We're emphasizing that character line by kicking the surface up a little bit. We're building the sculpting surface with the boundary surface, 2 profiles in direction 1, just sketches. Finally, that other sketch profile in direction 2. We're going to create the corner transition with the standard fillet tool. We're going to use split instead of split line because it's way better for the parent-child in my opinion. We're going to clean up the corner by split lining it and delete facing to get rid of that little extra material. And we're going to complete that corner transition with the boundary surface. And here is the sculpted character line. Got that really nice kick up here. So let's take a look at the next surface I want to build on this enclosure. Like the sculpted front surface, we've got a little bit of a subtle kick here to emphasize that line. But we know I need to have a kind of planar face here for an LCD that's going to come into it. This is a planar face as well, but we need to build this transition. It's going to be a little bit tricky, but we're going to take a look at that so we have a really nice clean transition between those faces. So due to the LCD in this thing, I needed this face at 20 degrees, but I built myself a little bit of kick up. Ultimately, I probably should have dimensioned this another way. This should have been driven, and I should have had dimension over here showing how much flat I had for the LCD. Ultimately, it did come a little bit, but we surfaced it in anyways. It worked out. So the way I'm creating this rear face of the enclosure is with two surface extrude features, this guy, and then we're going to create the boundary surface that will create the blend or the transition between those faces. And getting out where the blend starts and stops, where these edges are, is the key to getting a nice high quality transition. So into SOLIDWORKS here. Perfect. So we're going to take a look at our rear surface. I needed to add a fillet here just because this thing is butting up against something else. Needed that fillet to match. So I'm creating my first surface. Let's just change the transparency of this body so we can see a little bit better what's going on inside. I'm going to create the second surface in pink. So we've got the green and we've got the pink, and now we've got to build the transition between the two. So what I'm doing is using the surface trim tool, and how I'm picking where those edges are, I have a style spline sketched here. The arc determines the size of this transition, but ultimately we have this nice edge. So I had to play with this a little bit. I set up the size of this, and ultimately I adjusted it a couple times, which changed the angles here, because all I'm doing is connecting the end point of this fillet with the end point of this spline. Likewise over here. So the bigger this is, the more this angle changes. Also where this point is affects where this spline is, and I found that I had to kind of dial it in, get the right size, because otherwise the surface might look a little pinched. This surface did take a little bit more work. So I am setting up the curvature to face here. Because the surface is so large and it's changing in direction far more than this example. This example was relatively, it's not linear, but it's kind of following the same shape of the surface. It's just wrapping around. This surface here has a lot of different change in shape along its sides. So I set up curvature to face, and I increased the tangent influence to 100. And if we turn on our curvature combs, I'm not entirely happy with what the surface is doing up here. It's got this big spike going on. Ultimately, I did end up filleting that edge, and that kind of went away. So don't necessarily trust the curvature combs that SOLIDWORKS gives you in the feature. Use your eye. So if we were to hide this body, we're going to knit this together so I can make it the same color. And there we go. Now we've got it the same color. Let's use the zebra stripes tool. So we can see the zebra stripes actually look really nice over this. Nice smooth transition. And if we were to turn off our edges, you know, really nice transition. So I'm not going to rely on the fillet tool here. I prefer to just kind of manually build my transition. Maybe if I set up a variable radius fillet, I might be able to get something that works between here. But I find that just generating the edges, using the splines, and then building boundary surfaces between them is a way better and way cleaner way of creating geometry rather than relying on the fillet tool to build these kind of blended transitions between faces. Getting it into the model was super simple, just used another cut. So we're sculpting away the material. And once again, because I want to have a nice clean model, we delete that and we're done with this transition. So just to recap, the way we went about building this, we shaped the blend with the spline tool and the fillet tool. We built transition between them by using the line tool. We're just going to trim those surfaces back. Now we're coming in with the boundary surface, curvature to face, and that tangent influence is required to kind of pump up the surface and have it look nice. So we're lastly going to finish this example by looking at how I built this sculpted corner here. And this was a situation where I didn't have quite enough material to work with. I actually had to add a little bit of material to the model. This one. So one thing I want to show you is the power of split. So we're going to roll up the tree a little bit higher. So I created a surface that allowed me to split this body in two. The split tool works with planes, sketches, and surfaces. So once I split it, I've got the orange body, I've got the gray body. And the reason I did that was I want to go and fillet this corner. So I've rolled up before this split, and let's grab the fillet tool. One nice option they added in 2016 was the asymmetric fillet tool, which I think is a kind of nice way of creating blended transitions that just look a little bit different. So let's pick this edge. Actually, I want to go the other way with it. And once the fillet builds, the fillet propagated farther than I wanted. I ultimately want a nice straight edge here because I'm going to come back in and build this transition down. This is not the shape I want. And that's just the way the fillet tool works. It's got to find some way to end. But what happens if I split it and then drag the fillet down this way? The fillet stopped. Why did the fillet stop? Well, the fillet can't continue on to the other body. And so because I have this extra face in the model, the fillet's going to stop there. And now I've got this sharp edge here that I can come back and later fillet and then blend all this stuff together. But just like I said in the last example, I don't necessarily like relying on the fillet tool. It kind of really kicked up here. I don't like the way this tangent edge is looking. So instead of using the fillet tool, I'm actually just going to use a standard extrude cut. So I've got a sketch on the front plane, and what I did was I converted this edge in, I converted this edge in, and then I added my points, shaped by spline as required, and then cut it away. And what that did was generate a brand new edge for me here. So we now need to define this next edge because I want to blend this shape into this shape here. It's a matter of a second sketch. Same thing we've seen before. Style spline tool with the equal on everything to build that nice G3 connection, entirely parametric. And then we're coming in with the boundary surface. So instead of relying on the fillet tool, and here I didn't select tangent or curvature to face, and I didn't select curvature to face here, and there's a reason for that. Look at these red curvature combs. They look really, really nice. We've got that gradual fade in. I'm going to add curvature to face. Now there's a big divot. They actually inflect a little bit. My surface isn't nearly as nice by adding curvature to face. So just because you require curvature or continuous between the surfaces, don't necessarily just hit the button in SOLIDWORKS and assume that it's going to give you the right result. Just use the curvature combs, use the analysis tools that are built in, and we build a much nicer surface, a much cleaner transition. Now it's just a matter of coming in and knitting. And then once I've built this area of the model, I'm going to rotate back over here. We're going to take a look at how I built this final corner of the model. So I needed to add a little bit of material to the model, so I created a second body. I didn't merge it in. And then I shaped the material with a surface cut. So here we can see I'm using solid features to generate new edges in my model that weren't there before. Because what happens when I combine this in, we can see the size of this face, right? And then when I combine one more feature down the tree, bam, new edges into the model. So instead of using split line, I'm just extruding or adding material to the model, generating new edges. We can see I've started to define this transition. And this was a situation where the fillet tool actually gave me something I wanted. So instead of having to try and set up a complicated surface blend here with a 3D sketch or maybe a projected curve to get this edge, the fillet tool did actually a really great job. I used the asymmetric option to kind of dial it in, and I was actually really happy with what this looked like. So just because in this example the fillet tool didn't work for me doesn't mean in another portion of your model you might get a great result with the fillet tool. I really like this curve. It's a nice smooth transition from here to here. And I think we know what's coming next. Boundary surfaces. So we've got a boundary surface here. In gray, we've got a second boundary surface. So one thing to note here, if I just generate the bounding surface between the original edges, this surface, or this edge of the surface, is going to consider this face, which is planar, so it kind of comes out straight, and we get a bit of a waviness to our surface. And what this can ultimately, why this matters, is the underlying math that defines the surface is referred to as the UV curves. One way we can see these is if we turn on face curves. So I want to try and keep the face curves of my model as straight as possible. I don't really want to have this waviness in. So one way we can go about doing this, I'm not going to use this surface here. I'm going to create a 3D sketch, and I converted the edge in, and I grabbed the endpoint, and then I dragged it out. So we can always do that with converted entities. I added a construction line that was parallel to the right plane to fully define this. And one cool thing about using the 3D sketch in a boundary surface is even though this 3D sketch is longer than this face, and it's not an edge on this face, I can actually add curvature to face. So if you convert an existing edge of a surface into a 3D sketch, you can still add the curvature to face option. So I'm coming in to complete this transition. One thing I like to do is have really clean corners, so I extend the surface a little bit, and then I trim it back. So now I've got this edge going to, or this vertice going to this vertice going to this vertice, really clean transition. And we're coming in with the surface fill. I tried a boundary surface here and it didn't look quite right. Sometimes surface fill just does a better job than boundary surface for whatever reason. It's trying to rebuild here. There we go. One nice thing with surface fill too is that I can merge into and create solid. I believe they added that feature to the boundary surface, but I've never actually used it. That functionality has been in surface fill for a very long time. So quickly going back, see this fillet here, we didn't really like how the fillet terminated, so we can control the fillet terminations by splitting the model out and ending the fillet prematurely wherever you split. It's a great way for adding problematic fillets as well. We set up the blend by cutting that material away, generating this new edge that wasn't there before. We're creating a sketch to define this perimeter, and then finally dropping that boundary surface in. And we're going to evaluate our connections. Just because we want curvature to face doesn't necessarily mean we need to hit the button. Use your eye, use your best judgment, get the surfaces that you want, not the surfaces that SOLIDWORKS gives you. And the final sculpting, take a look at this. We need to add some material. Why are we adding material? Well, A, I needed a little bit material to sculpt with, and B, I needed to generate that new edge that wasn't there before. So instead of using split line, just extrude into the model. That asymmetric fillet, new in SOLIDWORKS 2016, kind of useful for creating more sculpted kind of transitions that look a little bit different rather than just a standard equal fillet. We're using that boundary surface, pulling it back. I can still make it curvature to face. And why? Because the UV curves. So the UV curves of this surface are very straight compared to the UV curves of this surface. And when we're surface modeling, we want to aim for that as much as possible. So we're going to move on to another example, freeform surfacing. In the last example, we had solid material that we were working with. We were able to sculpt it. We had edges and faces that we could use in reference. Here, we're going to use an example where we don't have anything. I'm going to have a little bit of a reference. I'm going to model this handle on this handheld flashlight here. And before we're going to start to model, I need to have a rough idea of where I need to build sketches and planes because I'm not going to have any solid geometry to build on. It's going to be way easier for me to surface this from scratch rather than build solids and cut away with it. And so I find it's always better to break the patches into smaller surfaces. Remember, the surfaces want to be lazy. They want to be relaxed. Don't try to do too much with one surface. And so by identifying where you think the surfaces should be, it's going to be way easier when we jump into SOLIDWORKS and start generating curves. One way I find of easily generating 3D curves in SOLIDWORKS is the projected curve functionality. So the way this works is we roll down the tree. I've kind of roughly identified the midpoint of the handle, and this is kind of going to become the silhouette point when viewed in this direction. So I sketched out what I wanted the handle to look like on the side. Then I sketched out a line here, and this purple line is actually a 3D sketch. So using the projected curve feature, I now have I now have a 3D curve in space. This is a great way of easily creating 3D curves because we're all familiar with 2D. So I've got a sketch right here, I've got a sketch here, and now when we rotate the view, I've got this nice 3D curve here. So here we saw that reference surface that I had mentioned before. This has the correct 2 degrees of draft for the parting line, because we're going to have 2-part clamshell on this flashlight. And now we need to start generating more sketches. And we need to create some planes here. So I have a bottom plane to define kind of the base. Ultimately, we'll fillet it into this model. And then we've got a handle below the trigger area. We're going to start with a couple sketches. And what I actually had to do here, I did use the split line to split this into 2 new edges here. So let's take a look at this orange sketch. This is pretty simple. I've got a style spline made tangent here to the reference surface, got that 2 degrees. I added a point on the style spline to lock it here, and I pierced it to that 3D sketch. So here I didn't have anything to start with, but you can kind of see where I'm going. I'm using 2D sketches on the kind of the default planes to generate 3D curves, and from there I'm creating more planes to generate 2D sketches to paint the outline of my surface. So I've got the orange sketch, I've got the blue sketch, I've got the pink 3D curve, and I've got these 2 reference edges of the draft reference. So now, boundary surface once again. So we're going from this profile, just turn off these curvature combs, make this a little easier to see. We're going from this edge, passing through this edge, passing through this edge, completing the surface, and it's following the sketches in direction 2. So there is the first portion of the handle, and let's move up. So this was the easiest, simplest surface. I know I needed to have a nice grip area to hold on to, but now I've got to transition the handle into the trigger area. I've also got it, F. Let's go back. I've got to transition this curve all the way up here somehow. So we've got to continue to lay out some surfaces. So finally, I've got this one kind of point here. We can see that I've got this sketch that transitions to this existing model edge. So I developed a sketch here. Oh, this is just a converted sketch. So one thing I'm working with here, just so that way it's easier for me to find the sketches, is the flat tree view, so nothing's absorbed. Normally these things are all kind of living in folders, but the flat tree view, all of the sketches are here for me to easily show. So I know that I need to have a flat area for the trigger to stick out through and grab onto. So we're going to use a surface extrude to build that, because ultimately it's going to be planar. This kind of doesn't really matter. We're going to trim this away. And now I've defined the shape of the trigger with a sketch on the front plane. Front plane, not right plane. And now I'm going to create a flat for the trigger. So that way we got a nice little trigger to turn this flashlight on and off. Once again, I've got new edges that I can work with. So I knew that this had to be here, so that's why I defined it first. It's going to help me with laying out the curves that dictate the rest of the shape of this handle. Rolling down, we've got another sketch. And this sketch is kind of going to be our last kind of reference. So we're passing through that 3D projected curve that defines kind of the silhouette, the midpoint of that handle. I've got an arc. Remember, arcs are your friends too. They're really easy to define geometry. They stay black all the time. So instead of just necessarily sketching one big spline and trying to control the whole thing, I find it can be sometimes easier to sketch an arc as required and then make the here equal curvature to the arc. And then I've used the pierce relation to lock this sketch segment onto this line here. So you can kind of see where I'm going with this. I'm creating another set of 2D profiles. And now it's just going to be a matter of dropping additional surfaces in. So this surface was pretty easy to do. All I had to do here was grab this edge, right? Grab this edge, and then this edge, and this edge. So we're using the 2D sketches and our 3D curves to build kind of 4-sided outlines for a boundary surface and then connecting the boundary surface. We're using the constraints as required, in this situation, curvature to face, tangency to face to ensure that 2 degrees of draft. We don't need a relation here because I'm just making to a sketch. And we're going to continue. We need to, ultimately, I showed before how we can use the boundary surface to get ourselves out of trouble, this big 5-sided patch. But one thing I found was that you need to tell the boundary surface what shape it should be. So it's advantageous to have a reference surface. So instead of making the surface fill just contact to an edge, we want to make it tangent or curvature continuous to existing geometry in the model. So here I'm using the boundary surface, and one nice thing with the boundary surface is it has these little endpoints. I believe they're called connectors. So normally this surface would be from this whole edge to this shorter edge, but if I grab the little endpoint and I can drag it up and make my surface shorter. So after I built the shorter surface, I'm going to use the curvature analysis, and it looks pretty good. But one thing I found is that these three-sided boundary surfaces, this unsupported edge, it's kind of flapping in the wind, it can have a really sharp jump in curvature, almost like a little ripple in it. So I find if you are creating those three-sided boundary surfaces, build them a little bit bigger than they need to be, and then trim them back. And now you've got nice, clean geometry through here. So the last little bit we're going to need is we've got direction for our surface fill on this edge. We've got direction on the surface fill on this edge. We've got direction here. I've got direction here, which is the draft reference, but I don't have any direction here to shape it. So instead of making it contact, I'm going to help the surface fill out a little bit. And the way I'm going to do that is creating a little guide surface. And the way I do this, 3D sketch, and I just grab a line here, sketched in the 3D sketch, and I make it tangent to this edge, and I grab the second line and I made it tangent to this edge here. And now all I'm going to do is build a little boundary surface or a surface lot between them, and now I've got a little helper, a little guide surface for the surface fill. So now the surface fill is going to take direction from this surface instead of not having any idea of what it needs to do when it contacts this edge. So this is a really good best practice when using surface fill. Try to have geometry on all 5 sides. Sometimes it's not required, but we do want to try and guide the surface fill as much as possible. So setting up this surface fill, we're using, ultimately I did massage this, but we're going to turn this back to tangent. So I'm grabbing all of my different edges, tangent, 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 tangency on all edges, built the surface fill. Oh, no, I did want to set those 2 edges to tangent or from curvature. And now we're going to see why we set everything tangent on the surface fill first. And then we're going to use the zebra stripes to evaluate. So right away, I can see that on this edge, I don't have a curvature connection because even though the line is connected, there is a break here. So I know that I'm going to need to go in and add curvature to this edge. So I'm going to continue to rotate my view and see that maybe over here, this edge looks pretty good. This edge is definitely not the best. And then this all looks pretty good. So I think I can leave tangency on this edge. I just need to go in and adjust curvature on that one top edge. So turning off the zebra stripes, we'll edit our feature. We'll go in and we'll click through the list. Oh, there's that edge. And from the drop down, we'll pick curvature. Click OK. And now we're going to come in and further evaluate. So I have a much nicer connection up here. But one thing I'm noting is I don't really have a nice connection up here. What's going on there? So this is where the zebra stripes is really good at helping you to evaluate your model. There's really not a nice connection here. So let's go back in and look at this existing surface. And we're going to turn on the curvature combs internal to the feature. And let's move around. So ultimately, this does look pretty good. There might be a little bit of a spike here. So one thing that I found is that I don't really know what these things do, but sometimes you can use them to increase the quality of the surface. Global, I just sometimes will drop through the list. So 2next curve, actually, nope, doesn't really work. It created a bunch of bumps in this curvature comb. 2next sharp, didn't really do much. So I tend to keep this on global, but if I do notice a little bit of an issue with the surface, I will go back in and kind of go through this curves influence. I tried reading through the help menu to see what those things actually do, and it wasn't very helpful. So this is where I'm just going to try and use the zebra stripes again. So actually, no, I'm looking pretty good. I'm happy with the way the light is flowing over this. The part's also going to have some texture on it. It's not going to be a mirror part. If you're ultimately going to texture your plastic parts, you can get away with a little bit of connections that aren't entirely perfect just because that texture is going to help diffuse the highlights. If this was going to be a really, really shiny, high gloss part, I definitely want to try and get it as perfect as possible. So I've got the surface fill into the model. We're going to remove the faces that I didn't need. We're going to knit it in. And then finally, we're going to complete this transition. So this surface was pretty easy. Remember, four-sided, right? Going from this edge, I don't really know what it wants to be over here, so I'm going to leave it undefined, but I do know what these edges want to be. So I've got curvature on this face. So we're continuing this transition. Now let's take a look at this big face here. So one thing I find that is helpful, we're going to go a little bit farther down the tree, is building this big surface. So I'm going to start with a much larger boundary surface. So ultimately, I could have potentially created the boundary surface here because I have one profile that kind of is four-sided, but the shape is kind of extreme. It's really going around this tight corner here. Like I've got a straight line segment, I've got a curvature continuous fillet, I've got a straight line segment, whereas here I've got a really nice smooth kind of curve. Ultimately kind of three curves, here just one curve. So what I'm going to do is instead of trying to complete the entire transition, I'll just go from this edge to this edge and build a whole bunch of extra material. Really, what the surface is doing over here, I don't care. It's not going to be in the model. I'm going to build it large, and then I'm going to come back in with the surface trim. And now I just have a little bit of that material. But I didn't want to guess what the surface wanted to look like through here. So that's why I just built the surface bigger than it needed to be and let SOLIDWORKS tell me, yeah, this is probably what the curve should look like here, rather than setting up a plane and then explicitly sketching this with a style spline or the classic spline tool. We'll continue knitting into the model. And even though this is a four-sided transition, surface fill is great when you have an unnumber of edges or not equal. So you've got 1, 2, 3 edges here, going into one edge here. So I'm going to use the surface fill and build that larger surface and trim it back. One thing to be aware of when using the surface fill is that if the boundary is inherently four-sided and you have optimized surface on, it may build a loft between them. And the way you can tell is this mesh preview. When they got rid of the yellow preview, they replaced it with this. So if you see a really square grid, when you have the mesh preview on, you know you're getting that larger surface that's being trimmed back. If you have the mesh preview on and you see a set of meshes that kind of follows this edge, kind of follows what your surface is doing and it looks four-sided, then it's just building a loft. So the whole power of surface fill is when it builds large and trims back. So turn that optimized surface on, I find it doesn't actually optimize anything. So we're going to build the surface. We'll turn our zebra stripes on, always check as we go. And I'm really happy with that. I've got a nice clean transition. The light's kind of coming up my handle and wrapping into that blend area. Likewise, the surface fill did a really good job of figuring out the transition to that back edge. So surface fill, really, really powerful, and I find it works a little nicer rather than trying to force a boundary surface into a situation where we've got a nice smooth profile here and a kind of a really sharp corner here. Just the surface fill's ability to trim back, build that larger patch, gives us much cleaner geometry in my opinion. So we've only got a little bit more of the handle to do. We just kind of got this last corner. We're going to continue knitting our new surfaces into the model. Here I just had to add a little bit more material for me to work with. Here I built a boundary surface so that way I could trim this profile. I could have used a sketch, just the way I ended up going about it. But we're getting to a situation where we can almost finish this model. So I need to finish this transition. The boundary surface kind of gave me a lot of the flat underneath here, but I need to finally cap off this last little three-sided patch. So we know that the surface fill is going to work, but one cool kind of feature in the 3D sketch, and it's particularly unstable, so use it sparingly, is the spline on surface. So this spline is actually going to stay on the surface. I found don't try and do any kind of ups and downs with it. Just put it between 2 points, make it tangent to an existing model edge, and you're good. It'll stay stable. But if you start trying to do too much with it and have it go up and down, it's not really going to work, and it really overdefines itself. So just all I've done is made it tangent to this edge here. And if I want to generate a new edge on this, if I have a 3D sketch spline on the surface, I can do a split line and it will split that face for me here. Delete face, get rid of that extra material from that boundary surface. And there is my final three-sided patch. So I'm just starting with tangency on this edge, contact on these two edges because I want a sharp edge, that G0 connection. Turn on our zebra stripes, and I'm happy with that. So this was a situation where if we were to hide our sketches so we can see it a little cleaner, I really didn't know what I was working with. I know that I had this hard edge that the handle ultimately needed to attach to. Ultimately, I'm going to build some surfaces later to blend this into the base region of this flashlight. But I'm using 2D sketches to generate 3D curves. From there, I have an idea of where I need additional sketches. So I set up planes, here and here. I create my 2D sketches on those planes. I create additional planes up here as required, more 2D sketches, and then I'm using nice big four-sided surfaces here and here. The surface fill was going to get me out of this tricky five-sided corner, but I needed to guide it by creating this surface and that little extra helper surface here. To complete this tricky portion of the transition, I created a boundary surface larger than I needed to, and then I trimmed it back, and then I created that surface fill to get me out of trouble. Likewise, big boundary surface here, and then that three-sided patch is happily conquered and easily conquered with the surface fill tool to create that larger patch, trim it back such that I don't have that degenerate point, which could really screw up the situation when I start adding fillets in this region. So that smooth, organically shaped handle, we're going to use the surface features. Here is that projected curve. 2D sketch, 2D sketch, 3D profile. Create the planes, create sketches, create flat portions that we know are going to be in the model, planar surface, trim it back, continue building those four-sided surfaces between the curves that we set up, create guide surfaces for the surface fill such that we can tame what the shape of the surface fill looks like. Come in with that surface fill, slightly older screenshot here, the old yellow grid preview that I wish they brought back. And we're done. We knit it all in the model, and we build that handle from scratch because we didn't have any solid geometry to work with. Want to leave with one last little example, a little case study here, really freeform surfacing. I'm just going to include this quote because I really like it, getting the most of the best to the greatest number of people for the least. Charles and Ray Eames were a husband and wife duo that designed some of the most iconic furniture of the 20th century. You might have seen this chair before. They were ubiquitous. And I had this chair 3D scanned, and then I decided to build a model of it just because, why not? So this is going to be a really, really free-form surface model. In the drill or the flashlight example, I knew that I had, it had to fit in my hand. Ultimately, this has to fit a human body, but I don't have anything to start with. I have no edges. I've got to define everything myself. So in order to get this really smooth, organically shaped chair, this chair was designed in the early 40s or late 40s and early 50s, and they didn't have CAD then. They sculpted it by hand and they made the patterns by hand. So you got these really authentic, organic shapes that just because CAD is easy and powerful, we need to bend the CAD program to our will and not give or get the result that the CAD software gives us, but get the result we want. And so that's why we're resorting to surface modeling. That's why we need to know continuity such that we can evaluate the surfaces that we're creating and know that we're really generating clean, organic shapes with no imperceptible transitions between the various surfaces in the model. So here is the other instance of patch layout. To start a model like this, I got to plan it out. I need to know where the big flats are, because once I've got the big flats roughly the shape, it's an easy matter of creating blend profiles and building boundary surfaces between them. Those are the blue, the primary surfaces in this screenshot, and the aqua, the blend surfaces. They collect primary surfaces together. The last are the magenta faces, and those are transition surfaces that complete the different regions of the chair, and they're usually the trickiest, so we leave them for last. So building primary surfaces, what do they consist of? They consist of large, relatively flat, they're not flat, but the transition, the radius of curvature is relatively constant. They don't look like fillets. They kind of look like large, flat portions of the chair. The primary surfaces and the blend surfaces come next. The blend surfaces connect the primary surfaces of the chair, and these are mostly connected out of four-sided boundary surfaces. We want to have those nice clean boundary surfaces. We use curvature to face as required to build them. And then finally, transition surfaces, and these are four-sided boundary surfaces, or sometimes they're 3, 5, or more sided surface fills. That surface fill is a great way of getting you out of trouble. So the first thing I did in this model, and we're going to jump into SOLIDWORKS, was define the outer perimeter. At least I had something to go with. And this was a situation because the outer perimeter undulated so much that I needed to create 3 different projected curves, all from 2D curves on different planes, and then I connected them together. So into SOLIDWORKS, into this example, where are you? There we go. Ignore this surface here. So the outer edge, I've got my first projected curve, second projected curve, and you can see the different planes that the base profiles are on. Here and here, here and here, top and side, finally top and front. And then I'm connecting them together. I convert the projected curves into a 3D sketch, and if you are creating transitions in the 3D sketch, I always default to the original classic spline tool. Why? Because it's only defined by its handles. So I've added equal curvature here. The style spline tool is great. It has really smooth curvature, as we saw before, but all those additional little control points can be a huge pain to try and manipulate in 3 dimensions and really control the shape of the curve. Whereas the classic spline tool, its handle is locked, and you can only really move the handle. And sometimes you can't move it at all. Sometimes when you add the equal curvature, it won't let you add or manipulate the handle. But like I actually got the exact result I needed out of the box, so I didn't worry about moving the handle. So I have the perimeter. I'm going to ultimately, I created some, because this was a model from the scan, there's some additional surfaces that are required. So this is a situation where I needed to create a reference for the mirror plane. I'm only going to model half of this chair, and then I'm going to mirror it over, creating the large four-sided boundary surface. So here was a situation where I had a sketch on a plane, and then I had a projected curve over here. But I'm building that four-sided outline of my surface, and then using the boundary surface tool to drop surfaces in between. We're going to continue with the back of the chair and the side of the chair. And one thing I did do was I split the back of the chair up into 2 surfaces. Surfaces want to try and be as square as possible, I've found. So instead of having this surface have come from this edge to this edge, I split this up into 2 smaller surfaces. Well, why is that? And it all has to do with the UV curves that we touched on earlier. So here is this kind of layout theory of creating good surfaces. So if I created this surface from this profile in green, I have the UV curves are actually changing angles through here. So this is why I broke this up into 2 surfaces. I have a large 4-sided surface with really straight UV curves, really good flow, really high quality. And then I built a second surface here where I'm controlling the shape of those UV curves. I want the UVs to slowly start coming from this shape to this shape. I don't want them to be this shape down here. These want to be nice and straight. So by splitting the surface up into 2 smaller surfaces and making them curvature continuous here and evaluating using the zebra stripes and the continuity tools we learned about, we have much better UV flow of the surface, much better quality. So this is why we want to try and do as least with the surface as possible. They want to be as relaxed as possible such that we have the best possible flow of the surfaces. So continuing through the tree here, once my large flat surfaces are built, it's just a matter of dropping boundary surfaces in between. Curvature to face, and I'm using the tangent influence here to shape the surface and match the scan as required. One thing I needed to do here was create a profile. I wanted to actually have a little bit more control here. So an awesome feature in SOLIDWORKS that is little known. So I'm going to delete this spline and we'll rebuild it. So I'm going to go from this edge over here, but I don't actually, here I can select this surface edge and go equal curvature, but note over here I don't have any edge. So how do I get this spline to be equal curvature to this surface here? Well, there's a little trick. So I select the spline, I hold down Control, I select the edge, and I select the surface, and I now have two new relations. I can make sketch geometry tangent to faces and equal curvature to faces. So I'll hit that equal curvature button, and now I can go about and manipulate the handles and get the shape I want. And now I have profiles. So I actually have a profile here, I have a profile here, and I'm building the boundary surface between that four-sided network, continuing my transition. One thing to note was I'm going to unsuppress this boundary surface. So logically, we want to use the boundary surface here, right? We have a nice four-sided transition, and it needed to increase the tangent influence to 100% to get this to work. But if we take a look, adding the tangent influence 100%, it really didn't look good. We were trying to do like the surface or boundary surface just kind of gave up. We can really see that puckering along the perimeter. If we turn on the curvature, we've got a sharp spike here. So this was a situation where bad boundary surface, couldn't really do anything about it. So I used a surface fill instead. Let's take a look at our curvature. Way cleaner. Look at our zebra stripes. Way better. So if you do notice you have a really bad boundary surface, it's okay. Try the surface fill. You're going to probably get a better result. Once again, an example of surface fill getting you out of a tricky situation. So I'm going to continue to develop the form of this. These are all just boundary surfaces like we've seen before. But I have two really kind of tricky areas I need to get myself out of. I've got to transition this backrest kind of into this flat here. And I left it for last because I really didn't know how to get myself out of that situation. So I continued here with another four-sided boundary surface. One thing to note is that sometimes, regardless of how hard you try, you have bad curvature on a boundary surface. So if we increase the mesh density and we want to up the scale, I couldn't tame this boundary surface. See that spike here, how it dips in? I just couldn't get it looking clean no matter how hard I tried. Tried a whole bunch of things, so I gave up. So instead of trying to get the surface right the first time, I just trimmed it back. And now I got rid of that nasty portion. I've outlined an area here, and I'm coming in with that surface fill. The surface fill, I was amazed. This mesh preview is way out of whack. The surface fill matched the scan perfectly once I adjusted the curvature and tangency conditions as required. So now I tackled that. The last little portion is this corner. And instead of trying to do one big surface fill here, once again, a situation where I'm going to use a boundary surface to tame and shape the surface fill, and then I'm coming in with the surface fill. That three-sided fill, added tangency and curvature as required, and there is the chair. Continuing a couple more features, moved it over. I used thicken to generate the geometry, and one thing when creating hollow surface models, whether that be you've thickened them or you've used the shell to build the inside of your shape, is this check button. Shell and thicken, remember we're offsetting surfaces, and sometimes the math can get a little funky as the offset surface bunches up. And the check actually reveals an error. And visually, we can see the error on screen. And so this surface is just not going to work. It doesn't even look like what it should be. So if you do run into this situation, run check, and actually after a thicken or a shell, you should always be running check just to see if there's any bad geometry. Because general faults in the models means you might be able to add features to them, and 20 features later, everything just gives up. You can't do anything with your model. So to clean this up, I'm correcting the general fault by deleting those bad faces, building a 3D curve, and then creating new surface features in between. So just be something aware of when you're surface modeling. The math's getting way more complicated than just dealing with surfaces. Tools check is your friend when thickening and when using this shell feature. So jumping back into SOLIDWORKS real quick to recap. We're blending or connecting our primary surfaces together with the blends, boundary surface, trim as required to get four-sided surfaces, create blend profiles to build our boundary surfaces between. Once again, a situation where we had to increase the tangent influence. 3D sketch, they're your friend with the tangent to face or curvature to face option. If you do get a bad boundary surface, use the surface fill instead. Use those zebra stripes to evaluate your connections. Curvature display as well. Keep building surfaces. If you get a bad area of your boundary surface, really bad curvature, well, just trim it away. Challenging transitions. Surface fill gets you out of so many jams. Guide the surface fill with the boundary surface. Convert to solid with the thicken. Run tools check. Check your geometry. Clean up as required. Well, that's all I have for this session. If you like this, want more, feel free to check out some of my previous sessions. Will It Blend from SOLIDWORKS 2014, Surfaces and Splines from SOLIDWORKS 2015, Have a Seat from SOLIDWORKS 2017, and Fantastic Plastic from last year's presentation. They're all up on YouTube. Just search for them. If you like this session, please take a minute and use the pocket computer, grab the app, session surveys. The process is convoluted, I know, but your feedback is appreciated. I'd be happy to take any questions personally up here at the podium after the presentation. We will be putting the model files I showed today, plus the whole PowerPoint on the Damani Group website. Come grab a business card. It's got our website. All I ask is that you grab a business card. Please leave one for me. Thank you very much. I hope you enjoyed this session. Enjoy the rest of your day and enjoy the rest of SOLIDWORKS World.